Section 5 of Chapter 9 deals with simple machines. Machines are devices to make our life easier. They do things we can't do. They do things we don't want to do. Many times, the machines do work that we can't do because we're not strong enough. We can't exert a large enough force. So one characteristic of machines is what's called mechanical advantage. Mechanical advantage is defined as the ratio of the output force to the input force. So I apply some force to the machine and it produces an output force. Let's look at an example of a nail puller. Figure 923 shows a crowbar or a nail puller. In the figure, we are applying a force labeled Fi for F input, and that's producing an output force labeled FO. That output force is what pulls the nail out of the block of wood. Now, I cannot exert a large enough force with my fingers to pull that nail out of the block of wood, but with the simple machine of a nail puller, which is basically a lever, I can exert enough force, causing the machine to magnify that force into a large enough force FO to pull the nail out. So if I draw a free body diagram of this lever, we have forces on the nail puller, F input. We have a normal force where the nail puller sits against the wood, and the nail itself exerts a force on the other end of the nail puller. This force is equal and opposite to the output force, which is required to pull the nail out of the wood. If I look at the sum of the torques in this problem, I want to calculate torques about this point where the normal force is applied. I need to know where these forces are. The distance from the pivot point to where the input force is applied is called L sub I. The distance from the pivot point to where the nail force is applied is called L sub O. So now back to calculating torques about the pivot point. The input force creates a counterclockwise torque about the pivot point. The nail force creates a clockwise torque about the pivot point. Then rearranging this, we have so the mechanical advantage here is simply the ratio of the two lengths, the distance to where the input force is applied to the distance where the output force is applied. Here's an image of a 12-inch nail puller I pulled off the web. The way this works is I will apply a force to the handle. The nail puller will rotate about some point and pull a nail out of whatever it's sitting in. So my free body diagram looks like this. So this nail puller has a mechanical advantage of 5. That means it will take whatever force I apply to the end of the handle and create 5 times as much force on the other end of it. So if I push with, for example, 20 pounds of force up here, it will produce 100 pounds of force on the nail. Another common machine is the pulley. First of all, we'll take a single pulley. We have a rope going over the wheel of the pulley. In this case, the tension in the rope on the right-hand side and the tension in the rope on the left-hand side are the same. The distances to where those tensions are applied from the pivot point are both the same. And so the equilibrium condition here is again that the torques have to add up to 0. Now it's not very clear. I think this is Ti and this is To. Now one thing to note here, this To is a force on some other object below the pulley. The force on the pulley by the rope must go away from the pulley because, again, you can't push a rope. And we're looking at forces and torques on the pulley. So now let's calculate torques. Ti creates a counterclockwise torque. To on the pulley creates a clockwise torque. And because the two radii are obviously the same, a single pulley has a mechanical advantage of 1. It does not increase or decrease the output force. So I pull on the rope with 100 pounds of force, it's going to create 100 pounds of force on whatever this is attached to. But now what happens when we have multiple pulleys? In this figure, this is figure 926 from page 332. It shows some configurations of multiple pulleys. And in each one they give a mechanical advantage. They say mechanical advantage here is 2, in the second one is 3, and the third one is 4. How did they get those numbers? Well, they show you a little bit here in looking at the free body diagram of the pulley. Let me explain in a little bit more detail how we do pulley problems. The way that you do pulley problems is you want to isolate a pulley as a system. And so, for example, in this first one, I'm going to make this my system. So for part A, my free body diagram looks like this. So the tension in the rope needed to keep this in equilibrium is just half of its weight. So this pulley system has a mechanical advantage of 2. Let's assume, for example, that the block has a weight of 100 newtons. So in case A, I only have to exert 50 newtons to hold it in equilibrium, or to raise it at a constant speed. So I produce a 100 Newton force by only exerting a 50 Newton force. I have a mechanical advantage of 2. Similarly, in case B, my free body diagram will look like this. So in case B, I have a mechanical advantage of 3. Now, one of the things to know about pulleys is that the rope has the same tension in it all the way through its length, as long as it's the same rope. Here's an example of a problem that uses different ropes. So in this case, there's a rope attached up here, goes down to the pulley, wraps around the pulley, goes back up, and is attached to the body of the second pulley. The second pulley has a different rope that goes down around it and goes and attaches to another pulley. So there's multiple ropes in this problem. What that means is the tension in each rope is not necessarily the same, and in most cases will not be the same. So how do I solve this problem? How do I find out what force I have to apply to hold up this weight? It's the same process. Let's put some labels on here. Let's label this pulley A, B, C, D, E, and we'll label these positions up here 1, 2, 3, 4, and 5. Now, same procedure. Define a system. And when you define a system, you want to cut through the ropes. So here's the first system. Free body diagram, force W, the weight of the block, and then there are 2 ropes here that I've cut through, but they're the same rope. So I'm going to call this T1. It's the rope attached to position 1. Sum of the forces in the y direction equals 0, but I don't know what T1 is. Let's look at the next pulley. Free body diagram for the next pulley. There's a rope attached to the pulley itself, and that's rope number 1. The other 2 ropes are what I've called rope number 2. Continuing the process. Now notice for this one, cable number 4 is the one that has a tension of P in it. So this system of pulleys gives me a mechanical advantage of 16. I can produce a force of W by only putting in 1/16 of that force, by only exerting 1/16 of that force.